When we look at a beam of light, it may look simple. But within every beam of light is a story of its origin, what kind of substance it came from, and what kind of substance it might have passed through. Examining the physical properties of materials by analyzing the energy that interacts with them is called spectroscopy. The concept not only works for visible light, but everything from radio waves to high-energy gamma rays. It even works for ranges of molecule energies and weights. When we spread out a beam of energy or particles into a distribution, it gives us important information. Spectroscopy plays an enormous role in all our lives. It serves as the foundation for nearly all our technology, from heavy industry and electronics and computers to biomedical research and medical technology.
From a chemist's perspective, often we're interested in looking at the structures of molecules, so we can learn a lot about the structure of the molecule, how those atoms are arranged together. If we're looking at sort of a bulk material, we can learn about the materials or the compounds that make up that material from using spectroscopy. Things that we use in everyday life that are, actually use spectroscopy. So the barcode scanner at your grocery store is actually based on spectroscopy. The weather radar system uses spectroscopy to analyze precipitation patterns. If you've ever been in a hospital bed, the pulse oximeter, that uses spectroscopy to analyze the oxygen levels in your blood. Spectroscopists are used in all kinds of technological fields, anywhere from pharmaceutical analysis to analyzing the impurity levels on a silicon chip for a computer. We have spectroscopists that are looking at the molecular makeup of interstellar space. Really, we use spectroscopy for all kinds of types of analyses and supporting of technology and technological innovations.
As a professional organization, the Spectroscopy Society of Pittsburgh has promoted advancements in science and technology for more than 65 years. As one of the leading industrial centers for over a century, Pittsburgh found itself as a natural birthplace for such a professional society.
Well, anybody who worked in the field of applied spectroscopy or analytical chemistry, Pittsburgh was the place to be. And it was because of all the heavy industry that existed in Pittsburgh in the 20s, 30s, 40s, and 50s. For example, all of the steel mills in Pittsburgh had spectroscopy laboratories because the characteristics of steel are determined by the content of carbon and all the other alloying elements that are mixed with the carbon in making the steel out of pig iron, copper, nickel, chromium, various other things. And emission spectroscopy was the key to determining exactly what was in each batch of steel, and that's what determines the particular qualities of the steel batch that they're trying to make.
The Spectroscopy Society of Pittsburgh owes its existence to a pioneering physicist named Mary Warga. When war started in Europe in 1939, the demand for Pittsburgh steel surged. Mary Warga, a physics professor at the University of Pittsburgh and an expert on spectroscopy, became involved in the war effort by helping metallurgists ensure the quality of steel. She started organizing small meetings on applied spectroscopy that eventually came to be known as the Pittsburgh Conference.
After the war, she formed collaborative meetings with other spectroscopists so they could keep abreast of the new developments that were happening extremely quickly during this time period. She also developed courses, and she mentored thousands of spectroscopists in the area in helping them improve their craft.
Mary Warga was the founder of the Spectroscopy Society of Pittsburgh, and she was really a trailblazer for women chemists. She worked in the field of chemistry at a time when it was dominated mostly by men. And so she has made my path as a woman scientist and the paths of lots of other women much easier because of what she's done for the field and for women in the field.
Mary Warga's Pittsburgh Conference grew into an annual event known today as PittCon, a major convention that connects scientists, engineers, and technology companies from all over the world. PittCon serves as a world marketplace for the exchange of ideas and inventions, stimulating innovation and keeping researchers up to date on all the latest technologies.
Well, PittCon provides an opportunity for scientists from all over the world who work in laboratory research to keep abreast of the newest developments, newest techniques, newest applications. And it gives companies from all over the world that market to the laboratory science field an opportunity to display their newest instrumentation and their newest techniques. So there's a very strong collaboration between the exhibiting companies and the researchers that come to PittCon, and that collaboration goes a long way to developing new scientific ideas, new scientific applications, new scientific instrumentation.
The mission of the Spectroscopy Society of Pittsburgh, along with the Society for Analytical Chemists of Pittsburgh, is to encourage continued scientific discovery and technological innovation and to promote science education.
The two sister societies, Society of Analytical Chemists of Pittsburgh and the Spectroscopy Society, come together and host this world-renowned conference known as PittCon, or the Pittsburgh Conference. And the revenue stream from that conference enables us to really fund science education in our region and also throughout the nation.
The mission of the Spectroscopy Society of Pittsburgh is the promotion and education in the field of science in all respects. And they do this through monthly technical meetings where they bring in renowned scientists to deliver technical lectures for the membership of the two societies and also for the general public. They do it by providing science workshops at the elementary level, the middle school, the high school level, and the college level. They provide equipment grants at all those levels as well. They offer starter grants for new researchers. They provide funding for public television science programs for the Carnegie Library, for the Carnegie Museum. There's practically nothing that the societies will not do to promote science and science education.
My name is Mark Hubert. I'm a volunteer for the Spectroscopy Society of Pittsburgh, and by my normal working job, I'm an assistant principal for Chartiers Valley School District. Being in education, I've learned firsthand what these wonderful programs they can do, really help benefit students, benefit education, and help promote science in general. So we've been around now for over 60 years here, and over those 60 years, we have really kept to our mission of supporting science education. I can tell you the way that I first got involved with the Spectroscopy Society was through their elementary science Olympiad. And as I brought that to my school, I did it with about 250 students my first year. And it was a day where the kids just lit up and they shined, and they got to apply everything they learned in science to really fun hands-on activities and real-world experiences for them. And seeing how the Spectroscopy Society allowed us to have that opportunity through their grants and their ideas and their suggestions, it was a phenomenal experience for the kids, and it is something now that comes back year after year at the school. And the kids, the parents, the teachers, everybody looks forward to it every year because they know what a powerful experience it is for the kids. And when you just do that and you see the smile on the kids' faces and how much they're connecting to it, it's just probably one of the best feelings that there is, and it just really shows you what science can do for kids and how they can apply stuff and really enjoy that.
Okay. Okay.
You ready?
Yeah.
Ready? Is this on? It's on. All right. Well, geez. Nope, that's too high. There we go. All right. Good morning. Can everybody hear me? We good? All righty. Woo! Welcome. Welcome. My name is Callie Schaus. This is Susan Zawacki. We are the chairs of the Faraday Lecture, and we are so excited that you are here. I'm so glad to have you, because it's crazy to think about that 20 years ago, I was in your seats watching the Faraday Lecture, and it's what inspired me to become a chemistry teacher. So I'm so glad you're here. I hope you see some really amazing things. But anyways, welcome to the 37th Annual Faraday Lecture, presented by the Society of Analytical Chemists of Pittsburgh and the Spectroscopy Society of Pittsburgh. We are excited to have Raymond Euler here today, assisted by Ryan Recipio. Woo. We're so excited for them to present a wonderful program featuring exciting chemistry demonstrations. So Ray grew up in Pittsburgh and he graduated from North Allegheny High School. He first started to take interest in chemistry when he was in high school. From there, he continued his studies at the University of Pittsburgh. Now, he works at Pitt in Chemistry Department as the demonstration coordinator. In his job, he continues to explore his love for chemistry, just as he did as a student. But now he gets to be the one doing the demonstrations. Ray particularly enjoys captivating an exciting audience with each interesting demonstration. The show today is entitled Don't Blink, to remind you that visual observations are foundational to the sciences. So to be sure to keep your eyes open and don't blink. Thank you.
You're all too kind. So my name is Ray, and this is Ryan, and together, there you go. Together, we are Ray and Rye. We're going to bring you a show called Don't Blink, or as Ryan told me earlier, with all the wires, I might want to call this Don't Trip. Hopefully that doesn't happen. So we have a series of demos to bring for you. I hope they all work. I've been ironing them out, so we don't want to send you all home happy and excited with chemistry. So to start off, first demo we have is what's called the iodine clock reaction. Has anyone seen this reaction before? A couple hands, but a lot of you haven't seen it. So this will be a fun first demo. What we have, 8 beakers. What Ryan and I will do is I'll take the beakers from the back, pour them into the front simultaneously, and as the title suggests, don't blink. Let's see what happens. So I'm going to count Ryan and me down. 3, 2, 1, go. There we go. 4 for 4, off to a good start. So if we could put the slides up. So what was going on there, the iodine clock reaction, generally proceeds via the 3 steps at the bottom there, but the one we really want to focus on for this reaction is that last step. One of the ingredients in here is sodium bisulfite, and what that does is it prevents the iodine from forming from the reaction. As the iodine forms, the bisulfite quenches it, turns it back to I-, and this color change requires free iodine to form I3-, which is what will bind to the starch that I have in there. And so what I did with these 4 different solutions was I changed the concentrations. This first one was most concentrated, and I made them progressively more dilute as I moved around. This is a well-studied reaction. And so by changing the concentrations, we've changed the kinetics of this reaction, or the rate at which it was occurring, and managed, even though we poured them all in at the same time, to cause the final observation to occur at very different times. So that's just a little diagram of what was going on there with that I3 minus binding to that starch, forming the complex. So this was actually a segue into this next demonstration, which takes this a step further. This is called a Briggs-Rauscher reaction, which is a chemical oscillator. So we're going to take the iodine clock, and we're going to run it, and then we're going to reverse it, and run it again, and reverse it a couple of times. So I'm going to go ahead, add my second solution in. Don't get too excited yet, the starch isn't in there. And now we're going to add the third solution. And if we leave that sit for a little bit, we'll notice that that deep blue color will slowly fade away, back to the amber yellow color, and back to the blue again. And so this will continue for about 10 minutes cycling, so we'll leave that go. If we could pop the slide back up. So the idea behind a chemical oscillator is a chemical system, a series of compounds mixed together, where there are some undergoing periodic changes. Now the reaction itself is not oscillating to and from equilibrium. That would break the law of thermodynamics, but some of the intermediate components are oscillating back and forth in formation, and the rates at which they're forming might oscillate slightly, but the reaction itself is continually proceeding towards that final settling state, that final equilibrium. So in this case, again, that iodine species is that key species. The I3 minus is giving us that deep color. And so as we're building up our intermediate, you reach a critical concentration, and you switch the pathway from intermediate producing to intermediate consuming, and then that dissipates the color. When it hits a low critical concentration, it switches back to forming the intermediate again as it slowly moves towards its equilibrium. So those are the three solutions. The one thing of note with the starch in here, this would be a lot less exciting without the starch. Clearly we have that nice blue color change with it. One of the other things that's postulated is that the starch both increases the number of oscillations that occur as well as lengthening the time between them, most likely because of the I3 minus complex with the starch shown up there on the slide, making it slightly less accessible to be ripped back apart. It has to leave that structure before it can be broken back down. So while that's going, we'll move over to what are called the freezing reactions. I use that term somewhat loosely here. What I have is what appears to be just a clear colorless liquid. I could swirl that around all day. It's not going to change. But what I'm going to do, I'm going to add the tiniest little bit of crystal to that flask. And as I add that, crystals are going to start slowly forming. Might be able to see them crawling up the side of the flask. And the entire flask becomes solid over time, which I think it's probably safe now to turn this upside down. So what's going on in this flask? What I have in there is a solution of sodium acetate. And so if we pop this slide back up, generally our compounds dissolved in liquid are categorized into 3 different classes. You either have an unsaturated solution where more things can be dissolved in it. You haven't reached that saturation point. Saturated solution where you've dissolved exactly as much solid as will go into a solution. Anything beyond that will not dissolve. You'll just get a pile of solid forming in the bottom of your container. And the third scenario is a supersaturated solution, which is what we had there. This is under special conditions. You can form this solution by heating up a solution and allowing things to dissolve beyond their capacity at room temperature. And then if you cool it very slowly and make sure you don't have any sites, glassware, kicked out there for a second, any sites present in the glassware for the crystals to latch onto, you can keep it in solution. So it is metastable though. It will want to crash out, and if you give it that nucleation site, like I did when I added that sodium acetate crystal, it'll come right out of solution. So reaction is up there. You might have actually experienced this particular chemical reaction before. We are in November in Pittsburgh. It's starting to get chilly. Sodium acetate is a salt that they'll put in reusable hand warmers. So if you've ever seen one of those little plastic pouches with a liquid in it and an iron disc, you bend the disc, it provides the nucleation site and the crystals form. These are really nice because all I have to do to get that ready for another demonstration is heat it back up. It will dissolve in its own water of hydration again, and it's ready to go. So it is kind of a nice sustainable way of working with that rather than just something you use once and toss out. So heat to reverse. Second reaction. This one is called, this one is a reaction between barium hydroxide and ammonium chloride. And this one's gonna kind of be the opposite of the sodium acetate reaction, which generated heat. As, again, if you've used a hand warmer, you've experienced. This one's gonna do the opposite. This one's gonna take heat away. So I have a piece of wood that I've been soaking in water. That's kind of important for this particular demonstration. I need to make sure that there is liquid. I have a beaker and 2 solids. So just to show that I'm not doing anything crazy here, that beaker came up, right? The wood stayed behind, so we're not doing any tricks. The interesting thing about this reaction as well is starting with 2 solids don't mix very well. They don't have as much kinetic motion as something like a liquid or a gas. So I'm gonna have to give it a little bit of help to get this reaction going. And I also turned on my thermocouple so we can see the temperature right now is registering somewhere around 20 Celsius. So the question is, just how cold does this get when it reacts? Now, as I stir it, the solids are gonna start sticking together and it's gonna form a bit of a slushy because one of the components is barium hydroxide octahydrate, which means it has 8 waters on that compound, and as they react, it releases all 8 of those waters, providing its own solvent to speed up the reaction as it goes. All right, so we have a liquidy, slushy mess in the bottom now. I'm gonna leave that sit for a second or two. By a show of hands, who thinks this is gonna drop 10 to 15 degrees? Couple. 15 to 20? 20 to 25? 25 to 30? Does anybody think it's gonna drop more than 30 degrees? Should we find out? So we are at about 36 and counting degrees drop. So this is a very, very endothermic reaction. It takes a lot of energy from the surroundings. But wait, there's more. So What temperature does water freeze at in Celsius? 0. If we're at minus 16, minus 17, what should happen to the water on that wood? Should freeze, which means this should come up with the wood. So just to wrap that reaction up, the previous reaction released the energy. In this case, we're looking at the heat flow. Heat is now flowing back into that as it approaches equilibrium. So we have our little pictogram of that. But we're going to jump ahead to a different sort of category of reactions now. Mr. Recipio, if you would like to come and help me out. All right. So this reaction is the luminol reaction. Has anyone seen luminol before? Couple hands. So luminol is used in probably, I don't want to say it's a happy situation at all. It's used quite frequently in crime scene investigations for detecting traces of blood. We will not be using blood today to test this, as exciting as that would be. So one thing we have to add last minute is our peroxide, which is going to kick the whole thing off, but if I leave it sit too long, it will decompose and we'll all be sad because things won't react. There's our peroxide. 30% peroxide is really nasty. You don't want to get it on yourself. 3% is what they use for cuts and things, but yeah, that stuff's quite aggressive. So what Ryan and I are going to do is we're going to go ahead and pour these two solutions simultaneously, one into each of these funnels, and then they should mix somewhere around the joint at table level where they'll run over into a collection container. If it's possible, if we could dim the lights a little bit, thank you. This will show up much better with dimmer lights. Whenever you're ready, bud. Ready to go. Yeah, it does. So what you just experienced was what's called chemiluminescence. And so there's a bunch of different forms of light-forming reactions. I believe my slide actually says 3 previous reactions. I cut one out for time. But there are a bunch of different things. Incandescence is slowly kind of getting phased out. You don't really see incandescent light bulbs anymore, but that's light through heat. That used to be one of the most common sources. Chemiluminescence, the light source is coming from the energy of the chemical reaction itself. We'll also be taking a look at fluorescence and phosphorescence in a moment as well. Those are both typically stimulated by UV radiation. And then there's a couple others. There's others I haven't listed there. But in the case of luminol, what we had was a basic set of conditions with peroxide in there. The peroxide releases oxygen, which then reacts with the luminol species itself and creates an excited species. When chemicals get into an excited state, they don't hold on to that energy forever. It tends to decay in some fashion or another. In this particular case, the decay happens to be just the right energy to be released as some form of visible light to us. In this case, it was a bluish glow. There's some other variations on this that can produce a greenish yellow or a red, depending on what else you add to it. But this energy is coming from the chemical reaction itself. I had iron ferricyanide in there, so that was our sacrificial iron for the reaction to catalyze it. When it's used for blood detection, the iron comes from the hemoglobin in your blood to induce the reaction. Let's see how this feels. That should be pretty good. We'll give this a go. I think we have enough time to run this. I was debating whether or not to cut this from the demo. I think we have enough time though. And so I'm going to leave this sort of run in the background as we proceed to one or two of the other experiments. This is basically just taking what we did and turning it into an oscillator. If this is warm enough, you might want to turn it up a little bit. It should have about a 30-second period between glowing oscillations. Otherwise, it might take longer. So we'll kind of leave it as a nice little background bonus if it works out well. So we'll keep an eye on that and see if it does start oscillating over time. If this works correctly, we should see a faint blue glow coming from it every so often. Now, in the meantime, while we're waiting for that to settle in, we'll go ahead and talk about fluorescence. So I had mentioned when we did the first luminol reaction, fluorescence is another form of luminescence. In this case, I have a UV lamp. I have a bunch of different samples, and we're going to excite them and see what happens. I should also mention this lamp has two different wavelengths. So the first one I'm using is shortwave, which is 254 nanometers. I'm going to switch now to long wave, which is 365. And we notice that it glows much brighter under that long wave as opposed to the short wave. This starts getting into the realm of chemistry and physics, the quantum realm, saying that not everything is on a continuum. So this kind of illustrates that there are certain energies that are going to be better absorbed than others and allow for these excitation transitions. The 254 had a very faint glow, but there are other wavelengths that just won't. Obviously, room lighting is not causing that to glow at all. So you need very specific energies to cause these excitations. Now, another thing we can do is, which I'm not sure how well this will show up, so we might just want to stick with the insect on this one and see if that glows, is discussing the difference between, yeah, it's kind of hard to see in the lighting, the difference between fluorescence and phosphorescence, because they are very similar processes, but phosphorescence is a much slower process, and you might know phosphorescent material as glow in the dark. In the case of my fluorescent material, as soon as I turned the lamp off, the luminescence stopped. In the case of phosphorescence, it's pretty hard to see on this, is the wings on the insect went out immediately, but the body took a couple of seconds for the glow to decay. And that's due to what's called an intersystem crossing from what's the singlet state to a triplet state, which basically just means it's taking longer for it to finally release its energy. And so those glow-in-the-dark materials, those phosphorescent materials, are able to store the excitation energy for a much longer period of time before releasing them. Now, I do have one other fluorescence topic here to mention, and that is this idea of what we call a quantum yield. Fluorescence isn't perfect. We measure what's called the quantum yield by comparing how many photons are released to how many were used to excite it. And so I have a solution of tonic water, which let's just verify that is fluorescent. So it does glow. That's because of the quinine in it. And so what I'm going to do is I'm going to pour this into two beakers side by side. And I'm going to add salt to one of them. But before I do that, so we can see that the fluorescence is ultimately equivalent between the two. It was the same source of tonic water, so it's offering up about the same level of intensity. But if I go ahead and add a little bit of salt to one of them, in addition to foaming up, as that calms down and the bubbling stops, we should be able to see there's very little, if any, fluorescence in the beaker that I just put the salt into. So this is a case of what's called fluorescence quenching. For fluorescence to occur in the first place, you have to have sufficient energy being released in that relaxation that's in the range of visible light. By adding that salt, what I did was I offered another path for that energy to be released in a non-radiative way. And so the energy's still there, but instead of relaxing out to release the light, it's been transitioned somewhere else, and that halide salt has quenched out the fluorescence. So who wants to see me burn a gummy bear? All right. Lucky for you, I have to have one. So this will take a little bit of time to heat up, so I'm just going to get this set up, and then I'll talk about what's going on as I'm heating it up. Get the torch going. There we go. So what I have is a test tube with potassium chlorate. Like the peroxide, the chlorate's going to act as an oxidizing source, a source of oxygen for this reaction to happen. And then the gummy bear is going to be my fuel. Now, has anyone heard of the triangle of fire before? A few hands. So, triangle of fire talks about the three ingredients that need to go into forming a sustained combustion reaction. You're going to need some source of energy or heat, which I'm applying, some type of oxidizer to provide the oxygen for it, that's my chlorate, and some sort of a fuel, which I have sugar. So I have all the three things needed for a sustained chemical reaction, combustion reaction here. This is actually quite similar in some sense to when you eat the gummy bear, although it's going to be much more violent. Where you take the sugar in, that's the fuel, you break it down, you get your carbon dioxide and your water, which are typical combustion products. But again, we're going to add a little pizzazz to it. The other thing to pay attention to is I deliberately chose potassium chlorate as opposed to sodium chlorate. You'll see why once we actually run it, and we'll discuss what's going on with that. We're getting there. This is always the worst part, is waiting for this to melt. Well, I'm glad you all find this exciting. So how about this? Whenever this melts, how about you guys count me down, give me a 3, 2, 1. I'll let you know when we're ready to do that. All right, I think we're good. You guys want to count me down? All right, so can we put the slides up? So probably noticed a couple of different things occurring from that reaction. We have flame, so we have light and heat coming off of that. We had a color. Does anybody want to tell me what color we saw? Yeah, a nice sort of lavender pinkish purple color. And as that wafts around, you'll probably get a bit of a smell of sort of roasting marshmallows. That's caramelized sugar in there. So what we did in terms of the color was, that's why I chose the potassium. If I chose sodium, I would have had an orange flame rather than a purple flame. And this is due to atomic emission. So what we did was we took that salt with this potassium metal, we heated it up, we got it excited to the point where one of the electrons jumped up to a higher energy level. And as it relaxed down, that energy jump was in the visible range in that purple region. And so, again, with sodium, sodium lamps, I think at this point are sort of getting phased out in terms of street lights, but they used to be a very characteristic yellowish orange glow, which wouldn't have been anywhere near as exciting because it would have just looked like a regular fire rather than a nice sort of violet fire there. Elephant toothpaste. Anyone seen this? Yeah? That seems to be a crowd favorite. So what we have with elephant toothpaste, I have potassium iodide and some soap here, which I'm going to go ahead and add in. And then all we need to add is peroxide. So I'll go ahead and add that. Now, what goes on with this reaction is we're basically going to take the peroxide and decompose it. Peroxide's not the most stable molecule. It's going to want to break down into oxygen and water, but in the bottle, with a little bit of stabilizer added, it's not going to do that very quickly. So we're giving it a little help with the potassium iodide and with the soap is to trap the oxygen as it forms to make it a little more messy and a little more exciting. So let's just go ahead and see what happens as the peroxide decomposes. Now, I'm not sure if anyone in the front noticed. Did you guys see the steam coming off of that as well? This releases a lot of heat as this occurs. There is a much safer demonstration that you can actually do at home with this, not using 30% peroxide, using 3%, which you can get on the shelves. And rather than the potassium iodide, you can mix it with instant dry active yeast, and the yeast will serve as the catalyst for this reaction. So if you want to have some fun at home, make a mess, you can do it with yeast and 3% peroxide. So I want to take this a step further. We saw that from all the bubbles a gas formed, but I want to make a callback to this in a later demonstration. So go ahead and take care of that. There's going to be a few other combustion reactions occurring later and a few gases that we're going to collect. So this is to, hopefully, this works out well, show you one of the tests we can do to test for the presence of oxygen forming from a system. Same setup as before, but without the soap, so this shouldn't be anywhere near as messy. I have potassium iodide and water there. And what I'm going to do is I'm going to actually dilute the peroxide down a little bit. I tested this out the first time and it went a little too aggressively and left the container, which I don't want to happen here. So we're going to cut it about in half. And from the gummy bear reaction, we're going to see something very similar occur, but without the purple flame. So with the gummy bear reaction, our sugar was our fuel, the chlorate was our oxygen source, and we had heat from the torch. So what if I take those glucose molecules and instead of having them as sugar, I have them in the form of cellulose. So I have my fuel, I'm going to light it, so I have my energy, and if I react that, that should form the oxygen. Oxygen by itself, you don't really have to worry about. Unfortunately, oxygen is hardly ever just by itself. In this case, when I put it in the presence of heat and fuel, it's going to function as the accelerant for this. So I'm going to go ahead and get this ready. And as that forms the oxygen in there, you should see the flame start to really grow and accelerate that burning process. So you can see as the oxygen's forming, that flame is getting much more intense. Enough oxygen to make it harder to blow that back out. So oxygen functions as an accelerant for it. Hopefully we'll be able to actually see with this demo in a moment or two enough oxygen to actually get the splint to, actually let's see if we can reignite that. There you go. You can actually reignite the splint if you still have an ember and oxygen. But this will be a much smaller scale. We'll see if we can use it as a flame tester, if it's going to not cooperate quite as well for us. Let me actually put this on the tile. Now, before we jump over to that particular demonstration, though, there's two others I'd like to do beforehand, which actually we'll move these. While I'm doing this one, if you wouldn't mind starting to move those into the center. So just kind of line them up at the center of the table. While Ryan's setting those up, we're going to go ahead and talk about acid-base indicators and then see if we can get more fire. So this first one, all I have is water, universal indicator, which is a blend of acid-base indicators, and a little bit of sodium hydroxide in there to adjust the pH. to a high enough level that the indicator turns purple. So indicator molecules change color with varying pH conditions as the protonation and deprotonation of those molecules adjusts their structure and therefore how they're going to interact with light. So in this case, I have purple with universal indicator. That tells me this is a pretty basic solution. The pH is quite high in this. What I'm going to do is I'm going to go ahead and drop a chunk of dry ice, which is about minus 78 Celsius, so really cold. At room temperature, though, it's going to feel screaming hot to that dry ice. So when I drop this in the water, it's going to start boiling immediately. So we notice the bubbling. Again, dry ice is incredibly cold. It's subliming off there as it's sitting in the water. We notice there's vapors forming at the top, so most likely some water vapor coming in there, getting a little bit of condensation going on there. And the color changed as the dry ice bubbled through solution. When dry ice bubbles in, it's solid carbon dioxide. As it bubbles through the water and dissolves in the water, it's going to form carbonic acid and then decompose from there. So the carbonic acid is causing a change in the pH. So I had high pH from adding a basic compound in there, and the carbon dioxide ended up generating an acidic compound in the solution, dropping the pH roughly to about, if memory serves correctly, 4 or so, giving it this nice orange color. So this is just to sort of bridge the idea of acid-base indicators. We're going to use it with a couple of metal samples, which I will have to be careful with these because water makes this worse if it catches fire. Got my special fire extinguisher for metals. You basically just cover it up with sand and try to smother out the oxygen from it. And so I have 3 metals. I have magnesium, I have lithium, I have sodium. Sodium is highly reactive with the moisture in the air, so both sodium and lithium are. And so we have to keep them stored under mineral oil to keep that air and that moisture out. Now, before I drop them in, though, if we could pop the slides up for a second. To make meaning out of what we're about to do, I just want to discuss periodic trends so that we understand what's going to go on with these metals. So typically in chemistry, compounds are going to want to seek out 8 electrons in their outer shell, the exceptions being hydrogen and helium. And so the way they tend to achieve that is by bonding. That's why we have chemical compounds, is these chemicals are trying to achieve stability. They can achieve that stability one of 2 different ways. You can either share your electrons with another atom, covalent bonding, or you can rip off or completely give away your electron to the control of another atom, ionic bonding. So whether or not you have covalent or ionic depends on the electronegativity of the 2 different atoms that you were trying to bond. And most compounds fall somewhere in between the 2. We call them polar covalent. So to understand what's about to happen, periodic trends, we take a look at the periodic table. And so increasing electronegativity is to the right-hand side of the table and up to the top. All of these metals are on the far left, and the sodium and magnesium are actually lower on the table than the lithium. So this will start giving us an idea of their reactivities based on that. So these metals, they're going to want to give up their electrons. They're on the far left. If they get rid of 1 or 2, they can end up on the right-hand side of the table in a noble gas configuration. So the further left you are, the easier it tends to be to get rid of that electron. So in theory, that means that the lithium and the sodium should be quite reactive. The magnesium, we'll just have to see if that's more or less reactive than the lithium, because it is further to the right than the lithium is, but it's also lower on the table. So we'll see how that actually plays out. So I'm going to start with the magnesium. I'm just going to put a couple scoops in. Nothing too exciting happening. You probably can't see from out in the audience at the bottom. There is a little bit of pink forming, which as time progresses will hopefully start permeating the whole container. I have phenolphthalein in there. That's an acid-base indicator, and as it approaches a more basic pH, it'll turn pink. So what's happening in here, this tells me that the magnesium is reacting with the water to form some sort of a basic compound, so magnesium hydroxide is forming in there. So we'll go ahead with the lithium next. See if I can get a good chunk of this. And since it's stored under mineral oil, we'll pat a little bit of that down. And drop that in. And as the oxide on the surface, because even under mineral oil, you will still oxidize the metal a little bit, as we start breaking away from that, that should start speeding up its reaction. You might be able to already see some pink coloration starting to bleed through. There's a little bit of steam coming off the top, and there's definitely some bubbling as that lithium metal is skidding around the surface. Now the thing we have to be careful about is usually those are going to be putting off hydrogen gas. If you're forming the hydroxide, the hydrogen atoms, what's leaving, if enough of them meet up, you get hydrogen gas. If you get enough heat from the hydrogen gas, we've been over the triangle of fire a couple of times already today, you're going to get a fire on water. So sodium is our last one. Fingers crossed I cut a good enough chunk that it does actually burn. Oh yeah, move that over here. All right, so let's see what happens when I drop the sodium in. So we can see a lot more steam coming off of that. You might be able to hear some hissing up front. As soon as that hit, any of the oxide, the hydroxides, dropped off the surface, fell to the bottom of the container, immediately turns that deep pink color, and the sodium kind of starts skimming across the surface. It does not look as if we're going to get lucky today. That does not seem to be igniting. But on occasion, if you get lucky, you'll get enough heat from that hydrogen gas that it will actually start forming the flame on top of the sodium as it dances around the container. So looking at the three reactions, clearly sodium was the most reactive of the three. On occasion, there's a brave soul that will attempt putting potassium in there. Probably not the best idea at this venue. As you can see, the difference between even the sodium and the lithium, potassium is much more aggressive than that. You're probably almost guaranteed to have it ignite and possibly a minor explosion on your hands, dropping sodium in. The magnesium, however, wasn't all that exciting. So even though it was lower on the table, it's a little bit further to the right, and so it's a little bit harder to achieve that octet. You have to remove 2 electrons rather than 1. Now, if we went further down that second column, we would probably see some slightly more similar reactivity, but in terms of these, the alkali metals are going to be more reactive than the alkaline earth metals, again, just because of that ease of removing the electrons. And part of the reason that they're so easy to remove as you move down the table is as you add more and more energy levels and your atoms get bigger and bigger in size, it's kind of harder for that nucleus to see the electrons on the outside, so it's easier to pick them away than the smaller atoms where they're held a little more tightly in towards the nucleus. So this is an example of periodic trends using acid-base indicator. So I think we have 3 demos left, if memory serves correctly, if we could pop the slides up. Yep. So the last 3 are going to tie in with each other and tie in with this whole hydrogen-oxygen idea for combustion. So what I have here is called a Hoffman apparatus. I'm actually going to let this one sort of run itself for a bit, and we'll jump over to another demo and then come back in to check on this. This will take a while. But what I have here is a Hoffman apparatus filled with sodium sulfate solution with bromothymol blue indicator. Now, bromothymol blue under basic conditions is blue. Under acidic conditions, it's yellow. Right now it's green. I have adjusted it to be at a neutral pH because as I apply voltage, I'm going to attempt to split the water that's in there apart, and the reactions from splitting the water apart are going to generate acidic and basic components. So if this happens properly, are we bubbling? We are not bubbling. Oh. I know why we're not bubbling, because I didn't plug it in. All right, do we have bubbling now? Now we have bubbling. So remember, kids, stay in school and don't end up like me. So what we'll notice as this proceeds is one side is going to turn blue, the other side's going to start turning yellow, which conveniently also happens to be Pitt colors. So it's a nice little demo to do at Pitt. But this is telling me that the side that's turned yellow is forming acid. The side that's turning blue is forming base. And as those are reacting, they're also going to be forming gas, which if we could jump to the slides for 1 second. There are our reactions. So one side's forming oxygen, one side's forming hydrogen. And we notice that there should be twice as much hydrogen as there is oxygen. The other thing to note is the hydrogen reaction should be the side that produces the base, in which case that blue side by the end of this should have twice as much gas as our yellow side, which is forming the oxygen, which is the acid producing reaction. So we'll see at the end of it, we'll take a look at where we are with gas collection after we run our next demo, and then we'll try to do a little bit of a flame test to verify that one side is hydrogen, the other side is oxygen, using our trusted splints, and I have some test tubes to collect those gases. So before we do that, we'll leave that go. And Mr. Recipio, if I could have you for this one. This one I do have to be careful with. Yep. So I keep mentioning how careful we have to be around fuel gases. So naturally what I'm going to do is fill a big container with a fuel gas and then light it. Yeah, we can just get these out of the way now. So I have a bell jar, and the bell jar has an opening on the top, and I have it set on some blocks so that it's also open at the bottom. The only reason this works is because hydrogen, thankfully, is less dense than air. So I'm going to fill it up from the bottom. It's going to displace all of the air out of there. I have to leave this run long enough to actually displace the air. If I don't displace all the air, well, it's nice knowing y'all. So I have a stopper on top. I'm going to fill it completely with hydrogen so there's only fuel in this container, and I'm going to light it. What do you need for a fire? You need your fuel, you need your energy, which I lit it, but where's my oxygen? In the air around. It's not in the bottom yet, but there's plenty of oxygen at top where I lit it. So the flame's going to light only at the top initially, and that's going to start consuming that hydrogen gas. And as that hydrogen gas gets consumed, air is going to start coming in from the bottom. And eventually we're going to hit a critical point where we have a lovely 2-to-1 mixture roughly of hydrogen and oxygen. And when that happens, well, there's a reason I have the screen in front just in case, but we'll see how it goes. So let me grab the lighter. And there should be good visual indication when it's about to go. The flame, you'll notice when we start, should be pretty high. And as it gets tighter and smaller and starts moving down towards the container, that's when we should expect detonation to occur. So this should hopefully take about 30 seconds to a minute to fill up properly. And then Mr. Recipio will graciously move our giant fuel source away from it. What do you think, Rye?
Nervous.
Should we do it?
Sure.
All right. Yeah, if you want to go ahead, close the valve. Okay, wheel that away. Let's see what happens. So, we have a pretty large flame right now. It's definitely up above where the shield is. So there's no oxygen when we started in that vessel. I filled it properly again. Thank goodness I lived to fight another day. But notice the flame starting to get smaller and move in towards that container. And eventually, we get enough oxygen in there to set the container off. Also, if we could get a close-up shot of the bell jar. One of the things we mentioned is that hydrogen and oxygen react to form water. Kind of hard to tell when you do balloons, but when you have a bell jar and you can see the condensation actually forming on the rim, you can actually see that hydrogen and oxygen do form that water vapor from the reaction. So let's see how we're doing over here. Do we have enough to collect yet? We'll let this go a little bit longer. I will point out that at the moment it looks like we're at about 10 milliliters of gas on our hydrogen producing side and just shy of 5 milliliters on our oxygen producing side. So chemistry is working as it always works. We'll let that go a little bit longer. We'll start blowing up some balloons as that will be our grand finale for this show. So you wanted me to do the mix. So if you want to go ahead with that, I'll get this one started. Oh yeah, you gotta really like squeeze around the neck. There you go.
An awkward tension.
Looks good, yeah. String right there you can tie that off with.
If the wind's coming for us.
Yeah, no. The neck on this one's not cooperating. We'll adjust them as we get there. All right. So we have our balloons. Do we notice anything about the balloons? Any differences with any of them? I see some people pointing down. Yeah, so one of them's not floating. So what that tells us is whatever's in that balloon is either close enough to the density of air that the extra weight of the balloon is pulling it down, or that it's more dense than air in general. The other two are considerably less dense than air overall. They're able to carry their own weight plus the weight of the balloon up and allow the balloons to float. So what we're going to do is we're going to ignite each of these in sequence. And we're going to see the difference between each of them as we set them off. So I'll go ahead and clear out a little bit of space here. Excellent call, Ryan. It's going to bring over the trusty pole of ignition for my propane torch. It should be okay. So we'll start off with a red balloon. Now what we have in the red balloon is hydrogen gas, which is what we just saw from the previous demonstration. It's going to go a little bit differently than the previous demonstration. In this case, when the balloon breaks, where's the oxygen? In the air. It's all around the gas this time, rather than only at one small accessible point. So when I ignite this one, it should go off immediately, right? Here we go. How about pure oxygen? We saw what oxygen did to a flame, right? Does this seem like a good idea? No? Should we find out? What happened? No explosion. So if we could pop the slides up for a moment. Why did the first one go but not the second one? I have a little diagram up there of the composition of air. How much of the air is oxygen? Roughly 20 or so percent, 21%. Plenty to sustain a reaction. If I have a balloon that's purely oxygen, it needs a fuel. How much hydrogen's in the air? Doesn't even register, less than 1%. There's not enough hydrogen in the air for that reaction to sustain itself. So the oxygen balloon in isolation, not a big problem. But again, most of the time, you tend to have a fuel source somewhere nearby the oxygen. So that's why you see all those warning signs not to have flames next to oxygen. So we saw both gases separately needing to seek out the remaining ingredient to run the reaction completely. What happens if we put both of those ingredients into the same balloon in approximately the right ratios for the reaction to run, roughly 2:1 with hydrogen to oxygen? I would recommend that everyone cover their ears for this one. Okay, you want that one? All right. Anybody want to count down? Looks like we gave the ceiling a little bit of a dusting there. So you might have noticed some of the shrapnel from the balloon flew out towards the audience. Another thing to notice, that does actually produce a percussive wavefront. Some of the solution from this beaker actually received enough of a shock from the wave to splash up and out onto my little catch pad there. So stoichiometry is very important when running chemical reactions. The right amounts in the same environment will help a chemical reaction run much more vigorously. We'll go ahead and pass this off to you. All right, so let's check in and see, wrapping things up, how our Hoffman apparatus is looking. That should be plenty of gas to collect now. So we'll go ahead and I'm going to turn the switch off. And we'll take our final reading, looking at about 27 for my hydrogen and a little over 13 mils for the oxygen. So it's still in that roughly 2-to-1 fashion. So we'll go ahead and we'll do our tests for the gas. Can I ask Mr. Recipio to come and assist here? If you could go ahead and light the splint for me. So I've just collected from the side that in theory should have the oxygen gas. Now again, this may not be anywhere near as intense as when we did the elephant toothpaste demo with that. But we're going to let this burn for a second, get a nice little ember, and see if we can get this to accelerate, possibly reignite by jamming in there. Well, it kind of wants to, but not quite enough oxygen to get that to reignite. Flared up a little bit, not as exciting as the hydrogen. So we'll go ahead and we'll collect the hydrogen gas second. And if you could reignite that for me while I collect the hydrogen. We have our fuel, we have oxygen in the air. So we have hydrogen gas present in that other side. So I think a lot of today has been the triangle of fire. Again, fuel source, heat, and oxygen. That's pretty much it for the demos. I would love to field any questions. Thank you all for coming, for listening. And if we have enough time, maybe blow up another balloon. So does anyone have any questions in the audience? Yeah. Sorry? How long have I been teaching? Graduated what, 2015? I think I've been teaching labs, organic lab primarily since then, and the demonstrations have been, this is year 3 for me now. So still relatively new. What's up? Oh, do you?
Alrighty, can you guys please give Ryan and Ray another round of applause? We want to thank them so much for coming out today to the Faraday Lecture. I'm sure they're happy to stick around for a few minutes if any of you who did have questions and you couldn't hear them and you wanted to come up. That would be great. Teachers, if you would please remember to turn in your survey to the ushers on your way out. That would be wonderful. But thank you guys so much for coming. I'll see you around.